In chapter 5b, we're looking at finding the arc length of circles using both radian measure and degree measurement, and then we move on to finding the area of sectors using both radian measurement as well as degree measurement. So if we consider this circle of radius r, remember, what does it mean to have one radian? Well, one radian simply relates to the one radius, or basically it's asking how many radii can I fit around this circle. So the one radian would relate to one radius being covering the circumference of the circle. If it was 2 radians, then it would mean that we're dealing with the length of 2 radii. Or if it was 3, then it would be 3 radii. So if I'm trying to find the arc length L, it's the number of radians times the length r. If we were looking at it in degrees, basically we know that the circumference of a circle can be given by 2 pi r. So if I multiply that by whatever angle I'm interested in over 360, this is going to give me what percentage of the total circumference that I'm looking for. Similarly, for finding the area of sectors, so you can see that our two formulae are slightly different. Now, if we just quickly come to this page here, and we can see, so the area of a full circle is given by basically theta. So for a full circle, we know that the circumference in radians is 2 pi. So if I'm looking at for some percentage, basically I have to consider, well, okay, how many radians do I have over the full circumference of the circle times the area of the circle, because that will give me the proportion of the circle that I'm looking for. So basically when I'm trying to find the area of a sector in radians, it would be theta over 2 pi, because there's 2 pi radians in a full circle, times the area of the circle. We know that an area of a circle can be written as pi r squared. So you can see here that that pi and that pi would cancel, so we're left with half theta r squared. Or if we were working in degrees, then it would be what proportion of a full circle do we have when we're looking at this area of the sector. So it would just be the angle theta over 360 times pi r squared. So let's have a go at a few of these questions. Okay, so if I'm asked to find the arc length of each of the following shapes, so remember, arc length when working in radians is equal to theta times r. And if we come back to this shape, we can see that we have 1 radian and our radius is 7. So it's simply going to be 1 radian times 7, which is 7 centimeters. Which makes sense because remember, 1 radian says that we can fit 1 radii around the arc length, so it makes sense that that is just simply going to be 7. Okay, let's have a look at B. So arc length is equal to theta times r, and we've got 4 radians, and the radius is 3 centimeters, so that means that this 3 centimeters is going to fit around this arc length 4 times. So it's simply going to be our angle 4 radians times our radius, which is 3, which is 12 centimeters. Then finally, if I have 2 pi over 3 radians, then the arc length is going to be 2 pi over 3 multiplied by the radius, which is 6.2, which is 13 meters. In question 2, we're asked to find the area of each of these sectors. It's important to determine, well, is the measurement given in radians or degrees? They're all given in radians for question 2. So that means that I'm going to be interested in using A equals half theta r squared. So for this first one, we've got 3 radians and the radius is r. So the area is going to be given by a half times 3 radians times, then our radius was 2 centimeters, so it's going to be times 2 squared, which is a half times 3 times 4, which is going to be 6 centimeters squared. B. So I'm asked to find the area of this. My radius is 8 centimeters. My angle is 1.5 radians. So area is going to be equal to a half theta r squared. It's a good idea to write the formula that you're going to be applying so then I can see, just in case you make a mistake, maybe you can get partial marks. So a half times theta, which is 3 radians. Sorry, it was 1.5 radians. This question. Times r squared, which is 8 squared. And that comes out to 48 centimeters squared. Okay, I'm not going to do a worked example of question 3 because question 3 is exactly the same as question 1 and 2. However, they've just told us what the radius and angle are in words, and basically they want you to apply it to find both the arc length and the area of those sectors. So let's have a go at question 4 because it is slightly different. So find in radians the angle on the sector of radius 4.3 and arc length 2.95. I would start off by writing all of this information down. So the radius is 4.3 meters, the arc length is 2.95 meters, and we're asked to find the unknown angle theta in radians. So I've written my equation. Arc length is given by the angle times the number of by the length of the radius. So if I want to find theta, theta is going to be L over R. I divide both sides by R. And then I just substituted my values. So I've got 2.95 over 4.3. And that comes out to approximately 0.686 radians. In B, they tell us that the area is 30 centimeters squared. And they also tell us that the radius is 10 centimeters. And they would like us to find the angle of the sector. So we can apply our formula. A is equal to a half theta r squared in terms of radians. And let's just rearrange, so theta is by itself. So theta is going to be equal to 2 over 2a over r squared. 2 times the area over the radius squared, which comes out to 0.6 radians.